Hello and welcome to Analytics Nexus 2019, the premier virtual event for analytics best practice. This presentation is titled 5 Steps to Building an ML Process and will be presented by Gary Angel. This is one in a whole set of webinars of presentations you have access to beginning today. A few quick housekeeping items before I introduce this particular presentation. At any time, you can interact with this presenter or other presenters with questions and/or comments on Slack. The Slack address for Analytics Nexus is analyticsnexus.slack.com, and you should have received an email invitation to join if you registered in advance. If you didn't receive that email, you can find an invitation link to the Slack in the menu below, as well as in the resource list. Once you log into the Analytics Nexus Slack, you can find the channel for Gary Angel to engage. Also, you can engage with us on Twitter. Our Twitter handle is @analytics_nexus. Finally, for questions on Analytics Nexus or Claravine, which is producing this event, feel free to email us at info@claravine.com. This presentation will be presented by Gary Angel. Gary Angel is considered one of the leading customer analytics and digital measurement experts in the world. Gary is the CEO and founder of Digital Mortar. Digital Mortar provides comprehensive collective and measurement of the customer journey in retail stores. Previously, Gary led Ernst & Young digital analytics practice. Ernst & Young acquired Gary's last venture, Symphonic, in 2013. President and founder Gary grew Symphonic to be the leading digital analytics practice in the United States. Voted the most influential industry contributor by Digital Analytics Association. Gary blogs at measuringthedigitalworld.com. His book, Measuring the Digital World, was published in 2016 by the Financial Times Press.
About 6 months ago, my company started a major process to re-engineer some of our core technologies using machine learning. It was fun, it was challenging, it was really, really hard. And the goal of my presentation today is to give you a sense of what it takes to take a digital analytics process or any other kind of analytics process and re-engineer it with machine learning. Because I think the most interesting thing, and something I really hope you get out of this presentation, is that the hard part of the process wasn't building models. It was really changing all the things we had to do around the way we did business to make this work. Most of this presentation is going to be about the actual things we did to build that machine learning process. But before I go there, I need to walk you through why we needed to do it and why we were trying to do this particular task. So I'm going to start, and I'm going to run through this really quickly with a little bit of an introduction about what we were trying to do and why we were trying to do it. Our core business is understanding the way shoppers move through stores. And traditionally, the store has been a black box. Stores know how many customers come in. If you look up as you go through the door of most retail stores these days, you're going to see a camera that's counting how many shoppers come in. What else do stores know? Well, they know how much they sold. They know what they sold. They know how much it cost. They know how much they made. But everything that happened inside and in between those two things, that's a mystery. That experience has been a black box, and that's what we try to work on. Fortunately, in the last couple of years, a set of technologies have emerged which let you actually measure the way shoppers move through stores. Wi-Fi and electronic means can actually pick up on smart devices and geolocate them in the store. Video cameras and mobile apps can do the same kind of thing. These are the technologies we use to understand shopper movements. And these technologies let us answer a whole bunch of questions about how the store is behaving, where customers are coming from, where they go, what they like most, what they're engaging with in the store. It's fascinating stuff. All right, but to really understand how this fascinating stuff works, you have to understand a little bit about the kind of data we collect. Imagine that this store was a website. One of the things that you might think about is, well, how does a journey look? Well, a physical journey in a store kind of looks like this, a pathway through the store. Now, as we think about that pathway, one of the things we want to understand is where people are spending time. So here I'm kind of highlighting and color-coding the places where the shoppers stopped and shopped inside the store. If I take each of those areas and I think about what was there inside the store, you can start to see that I'm understanding more about the shopper and the shopper journey. And in fact, if you think about taking each of those sections, naming them, and saying how much time the shopper spent there, you get a set of data that looks a lot like digital analytics website data. That capability opens up a lot of really interesting analytics opportunities. The kinds of things that you do on a website, you can now do in terms of the store. And a lot of the analytics are strikingly similar. But as with most things, there are some big challenges to this. And to understand our machine learning problem, you have to understand a little bit about the data collection. This is a store planogram, a layout of a store, and each of the blue squares on this planogram mark the positions of an electronic detector. This is the way a store data collection technology is generally set up. Okay, so how does that work for us actually collecting data? Well, all of these devices are listening for electronic probes from a smartphone. When the phone signals, multiple detectors will pick it up. Sometimes as many as 10 or 12 different detectors will pick up a single signal inside the store. By comparing the difference in signal strength picked up on each detector, we can trilaterate the signal to figure out where the phone was. This is the process of understanding where the shopper is in the store, and it's really a simple, pretty basic exercise in geometry. Okay, that's the theory, but in reality, it doesn't work very well at all. We think that this kind of positioning just sucks, and believe me, it's because we've seen it work in the real world, and it just doesn't position shoppers very accurately. Well, why not? It's geometry after all. Well, one of the big confounding factors in indoor wayfinding is that signals don't come directly to the device. They get reflected, they get deflected, they get absorbed by walls. Everything is conspiring to make it hard for you to understand whether the signal strength you received at the detector was really representative of how far away the device was from the signal emitter. We found there was a second basic problem, and this one's really surprising. It turns out that our signal detectors almost never function at 100% efficiency. They spend a significant amount of time doing things like communicating the signals they've picked up. What that means is they miss a fair number of signals. Sometimes they miss signals even when the emitting device was very close to them and it emitted an extremely powerful signal. That's really frustrating because when that happens, the trilateration gets the signal position completely wrong. You know, when you put these two things together, the result is that geometric trilateration usually gets the shopper position wrong. Most vendors who do this draw a circle of air about 10 meters wide around the smartphone and say, hey, the shopper was somewhere in this area. Well, 10 meters isn't bad if you're doing measurement in an airport, but if you're trying to understand what a shopper is doing in a mall store, it is absolutely not good enough. And that's the fundamental problem we were trying to solve. What we wanted to do was dramatically improve our ability to understand exactly where the shopper was in the store. And the reason I call this a core technology for us is that every single bit of analysis we do after that is dependent on the accuracy of our ability to position the shopper inside the store. So that's the problem we want to tackle. Okay. Why machine learning for this problem? Well, I'll start by saying we had a lot of data. When we track those signals inside the store, we get literally millions of signals every day. These phones generate lots and lots of probes. So we have this massive data set of signals being detected at sensors. What's the problem? Well, the problem is that none of this data is useful. Lots and lots of data seems like a great thing from a machine learning perspective, Why isn't it useful? Well, the problem's a simple one, and it's not uncommon in machine learning. And there's a pretty good chance that if you want to engineer a machine learning process, you're going to run into exactly the same problem we did. Machine learning, most machine learning anyway, requires supervised data. What does that mean? Well, for the machine learning to really work, for the machine to learn, it has to know what the right answer is. Think about all that data we collect. We have millions and millions of rows of received signal strings from each sensor, but we don't know where the phone actually was. The machine can't learn and get better on this problem because it doesn't have the right answers. One of the biggest problems most organizations face when they first try to use machine learning is that often, not always, but often, they don't have supervised data. That was our problem, and it was a problem we really had to work hard to tackle. In fact, of the entire machine learning process reengineering, tackling this problem of building ourselves a supervised data set was the single biggest issue we faced. Okay, let's talk a little bit about our solution. Our solution was to create a manual calibration process. Basically, we were going to create data from the ground up, and it started with us actually building a mobile app. The mobile app was fairly simple. Its sole purpose in life was to record where somebody was in the store and then start blasting out signals to our electronic detectors. The second part of this was a calibration plan. We needed to let the people who were going to be carrying those phones understand how to navigate the store. The third part of this was to find the people to do that. And surprisingly, we used TaskRabbiters. This turned out to be super efficient. The process isn't super complicated. It didn't take an installer or an electrician or a data scientist. What it took was someone to walk around the store for a really long period of time carrying a whole bunch of phones. We actually made videos to help people do this, and then we hired TaskRabbiters, shipped them the equipment, and then had them walk through it. And it was surprisingly successful. Finally, we had to take that calibration data that we got, match it up to the data from the mobile app that told us where the calibrator was. Now we had a supervised training data set. We knew where the signals came from, and we had the signal strings as received by all the sensors in the store. This was our supervised training data set. It's pretty cool when you think about it. This is all the data we needed to do machine learning. And all it took was rethinking our data in and building a process that allowed us to collect the data almost by hand from scratch. But it took a lot of work to get there. The mobile app took work. The calibration process took work. Figuring out how to get the people to do it and how to train them, it all took work. But the end result was a machine learning ready data set that could actually be used to make the process better. All right. Step number 2 is testing and manufacturing data. And you're probably going to say, hey, wait a minute, didn't you just create data? We did. But here's the thing about it. We found that we had 2 problems with the data we created. Hey, the calibrations that we were running generated tens of thousands of rows. But one thing we found was that our blasting phones didn't exactly match the kind of data that we were seeing in the real world. So in the real world, what we were seeing is when we picked up observations on the sensors, typically, about 5 to 6 sensors picked up a signal. But when we were calibrating, about 8 to 9 sensors picked up the signal. And the signal strength that we were seeing was usually stronger in the calibrated data. That really worried us because it meant that our calibration wasn't perfectly reflecting the data we're seeing in the real world. If that's the case, our machine learning model isn't going to be a perfect reflection either. So what was our solution? Well, our solution was to build a data factory to use the data we had to create even more data. And our goal was to make more data for the machine learning process and make the data more representative. To do that, we actually used 2 different techniques. One technique we called time window slicing. We aggregated the data at different time window levels. Sometimes down at a 500 millisecond level, sometimes down at a second level, sometimes at the 2-second level that we were using for our real-world data. By refining the time window, we were actually able to cut down the amount of data inside the time window and make the data look more representative of what we were collecting out in the real world. We had one other problem, though. One of the things we found was that we weren't losing as many sensor signals, problem number 2 in the 2 big problems I gave you, in our calibrations as we were in the real world. The reason for that is we tended to calibrate stores when they were closed or not very busy. So the sensors weren't doing as much work, and they weren't losing as many signals. So we actually did something pretty peculiar here. We wrote a process that took each record and in some cases duplicated it, but in the process of duplicating it, it actually dropped 1 or 2 randomly picked sensor readings. The goal here was to create a machine learning data set that reflected the real world, and in the real world, we were losing those signal strengths sometimes. So we wanted to see what was happening if instead of getting the signal on 7 sensors, we only got it on 6, or we only got it on 5. This data factory, as you can see, allowed us to match our real-world data much more closely. And it had the side benefit of getting us a lot more machine learning training data to use. That made our models better. So in a lot of ways, this was a win-win. Okay, manufacturing data to create more data for your machine learning may seem like cheating, but it really worked very well, and it got us to step number 3, which for the analyst is the really fun part of the process. This is where you model and tune the model. This is where you really have fun as an analyst, and I'm just going to call out a couple things that I think are really important to understand about this. First of all, sometimes there's an assumption that with machine learning, the machine's doing all the work and the analyst doesn't really have to think about it. You just take that big old raw data stream and feed it into the machine learning and you're done. Well, that's not right, actually. A lot of times you really have to think about how you want to represent that data and what kind of variables you want to create. Just to give an example here, we're aggregating all of these sensor data by a time window. Sometimes a time window as large as 2 seconds. When we do that, sometimes we had multiple signals being received by a single sensor. So we had to decide how we wanted to represent that. Do we want to look at all of the signals? Do we want to look at the average signal, the maximum signal received, the minimum signal received? Well, we tried everything here. We tried the mode, we tried the median. We threw every variable we could at the problem. And I think that's not a bad approach, actually. One of the nice things about machine learning is that it's super efficient. The studios and the machine learning techniques that we're using are really fast and able to handle lots and lots of data and lots of variables. So in general, I think the right idea here when you build a model is to go big, include every variable you can think of to start with, and then gradually refine it down to see what worked. It turned out here that it actually didn't make much difference which of those representations we used. The models worked pretty similarly across all of them. All right, I'm hoping here to actually be able to give you a little bit of a sense of the model building process. I'm hoping we can dive out and actually show you some of the machine learning models that we do in Azure Machine Learning Studio. My goal here really isn't to teach you how to do machine learning, but it's just to convince you that with the data science studios available for free or widely commercially on the market today, that it's really, really easy to do this. It doesn't take a programmer. It doesn't take a deep data scientist. It's drag and drop interfaces that make it really simple to construct models.
I just wanted to show you a little bit of what it's like to work in a data science studio and give you a sense about just how easy it can be. Here I'm in Azure's Machine Learning Studio, which I use quite a bit. You can see it's a drag and drop interface. What I've done here is started with a data set, built a SQL query, then selected the columns that I'm interested in. You can see it's a lot of the same columns I've talked about. After that, I can shape the data using various metadata filters that allow me to specify what my label is, what my features are. I can tune variables, I can change their types, I can do basic transformations. And then I can come down and I can split my data. Here's where I create training data and holdout data. And of course, I can build models. One of the nice things here is you can actually have the studio try a bunch of different parameters around the model to see what works best. Okay, let's evaluate and run this model. So I'm going to run it. You can see it's really, really fast. We're not dealing with huge quantities of data here, somewhere between 40 and 50,000 observations. The overall accuracy of the model was around 85%. Not too bad. This is the confusion matrix. It's telling me where I predicted a shopper to be in the store versus where they actually were. For some areas of the store, I got as high as 95 or 96% accuracy. That's really good. And I can also see when the model got it wrong, what section it picked. And usually it's a right next door adjacent section. There are some sections that are a little more challenged, areas where maybe I have problems with either my calibration or my model. The confusion matrix is super powerful for tuning your data science. Okay. Let's suppose I want to try out a different kind of model. All I have to do is hook it up. I'm going from a multi-class decision forest to a one versus all multi-class based on a two-class decision forest. I'll run it, and then I'll look at the overall evaluation of the model. Before I had 85% accuracy, now you can see that's up to 87%. And if I scroll down in the confusion matrix, you can see that in some cases, I'm almost 100% accurate. That's pretty darn good. But you know, some of the sections still aren't doing that well. These are areas where I can continue to improve my model or check on what the calibrator did in those specific sections. Hey, there's so much you can do with these data science studios, from running in data sets, saving trained models. You can do all sorts of format conversions. There's a lot of data input and output. You don't have to be a programmer to use this. All the basic data transformations are available to you and are pretty simple to use. If we want something fancier, we do it in code, but you can do a lot in the studio. There's a ton of models across a lot of different model types. When you create a model, you can create an anomaly detection model. You can create a classification model. That's what I'm using here. You can also create clustering models. We do a lot of k-means clustering. And you can do regression models. We do that when we want to pick XY coordinates for something. If you really want to get sophisticated, you can do Python, R, and OpenCV libraries so that you can really extend the data studios to do fancy, fancy stuff. This is a really powerful tool. I'm going to show you here another one of the models. This is an XY prediction regressor, so it's a much more complicated model, and you can get a sense of how large the data flows can be when you're working in this kind of studio. The thing I really want you to see, though, is both how fast and easy it is for someone to put this together without being a programmer. And this is not unique. All data science studios these days bring similar kinds of capabilities. Hey, this is the easy and fun part.
Okay, that's how you build models in the Azure Machine Learning Studio. Now what I want to talk about is step number 4 in our machine learning process, checking for coherence. What do I mean here? Well, sometimes when you build a machine learning model, you're good. You can look at the training set, you can look at the holdout set, you can see you're doing really well between the two, and you're done. One of our challenges, though, and I don't think it's particularly unusual in the machine learning world, is that, remember, we had some issues with our calibration not necessarily matching the real-world data we came in with. Well, how are we going to be confident that once we built a machine learning model, even if it worked really, really well on that calibration set, that it was actually working just as well in the real world? Well, one of the ways we tried to tackle that problem was by building multiple different kinds of models. So, for example, we built a model that we called the out-of-bounds model. And the out-of-bounds model basically just looked at whether a shopper was inside a store or outside a store. If they were outside the store, we're going to throw them away. If they're inside the store, then we pass them on to the next model, which is the section building model. The section building model tries to assign them to a particular area of the store. Where were they in the store? Were they in men's jeans or women's lingerie or in clearance section? So that's really one of the core models. But once we do that section model, we have a third model we pass to, which we call the XY regressor, which tries to figure out the exact coordinates of where the phone is in the store. Well, with those three models, one of the things that we could do is actually check for the coherence of the models. So if we ran the out-of-bounds model, and then we ran the section model, we can look and see whether the section model said that someone was out of bounds, if the out-of-bounds model said they were out of bounds. And if the out-of-bounds model said they were inside the store, Did the section model put them in a section inside the store? That's what we were calling coherence. And what we were looking for was a high percentage of agreement between the various models. This turned out to be a really, really powerful indicator. You know, it's funny, but sometimes when we were building these models, well, believe it or not, we made mistakes, or the calibrators made mistakes. Calibration mistakes could be particularly devastating in this case because the machine learning just went right along and classified them. But when calibrators made mistakes about what they were doing, what we found was the coherence of the models got much, much worse. The XY regressor no longer agreed very well with the section classifier. So this turned out to be a really good technique for us to debug the process. And it's something that if you're doing machine learning and you don't have confidence about whether your results are actually reflective of reality on your production data, this is a really good approach for figuring out if you're doing it right and whether you're successful or not. Okay, I mentioned right at the outset that the biggest challenge we faced when we went through this whole machine learning process was probably operationalizing models. I think I contradicted myself there because I also said it was really hard to build that supervised training data set. Well, it was hard. Both of those are really difficult problems. But I've come to step 5, and what I want to emphasize about this is how important this is. So often we think of machine learning as a purely data science analytics kind of process. Well, it's deeply analytic. It is something that an analyst needs to do. It's something an analyst can have a lot of fun with. But here's the problem. You can do a lot of great data science and not be able to operationalize it inside the broader process. For us, as a small company wanting to build machine learning into one of our core processes, that isn't going to work. You know, we had all this data coming in on a daily basis. We needed to have it operationalized. Building the models and proving that we could do better classification and better shopper location wasn't enough. We actually had to have this running on millions and millions of rows every single day. Well, it turned out to be kind of hard, actually. You know, I showed you the Azure Machine Learning Studio, but productionizing things off the Studio turned out not to be as easy as we were hoping. There are ways to do it. The Studio actually supports an API-based interface, but we thought that that was slow and costly. We have really high levels of production data coming in. We didn't want to have to make an API call to the Studio every time we were doing that, and that also cost money. So what we looked for was 2 other ways to do this. We actually built 2 separate operational pipelines here, both of them in code. One of them is a set of Python code that actually took the Python machine learning libraries and recreated the models and built them out that way. The other we did using the ML.NET library. This is a .NET Core framework that Microsoft provides that's very similar to the model building out on the Azure ML Studio. This turned out to be really convenient for us because if we built something on Azure ML Studio, we could take it into the .NET Core code and be pretty confident that we're going to get similar results. We actually use both pipelines. Python in some ways has proved extremely convenient for productionizing a lot of what we do, but there are times when the sort of coherence and consonance between what we're doing in Studio and what we want to do in ML.NET is really, really convenient. Here's the bottom line on this, though. Don't start a big data science project unless you've thought a little bit about your operational strategy. We tried a number of directions here, several of which were disastrously unsuccessful. Make sure you have a path to operationalizing your ML models. Don't forget about this. It's not the fun part. It's also a part where the integration of developers and data scientists becomes extremely important. Listen, this isn't a big issue in my company. We have more developers than anything else, and we work really closely together. But in a lot of large enterprises, this can be a big challenge. Don't forget about it. Don't skip it. It's really, really important. All right, time to wrap up and summarize what we've gone through today. All right, I'm going to give you what I call the keys to the car. And I'm going to start by saying that machine learning is real. The opportunities are significant. We were really pleased with the way this project came out. We significantly enhanced our ability to locate shoppers inside the store. But it took a lot of work. This was a 6-month project beginning to end that forced us to re-engineer a lot of core things we were doing in the company, and it was hard. Second thing I want to talk about, in this data-rich world, and I made this point right out of the bat, we tend to assume we have all the data we need. What you hear is people talking about how they're drowning in data. But with machine learning, one thing we often lack is a supervised learning data set. You have to have a data set that has the answers embedded inside of it, or the machine can't get better. That often takes work, and sometimes it takes a lot of manual work for you to create that data. Just because that process is so manual, one of the nice things is you may find yourself with a smaller data set than you like, but you can use whatever data you can generate to create more data. We did that and did it pretty successfully, not only manufacturing more data, but making sure that the data we manufactured made our calibration more relevant and closer to the real-world data that we were collecting. You know, I want to emphasize that a lot of times, people who haven't done machine learning think the hard part is building the models. Not so! Data science studios these days, and there are a ton of them out there, make it really easy on the analyst. You know, some of them are kind of complicated, but a lot of them have brought great drag-and-drop interfaces to the table that let you really manipulate the data, build models, run them iteratively, and get the results in a super quick amount of time. I think of this not only as the most fun part of the process, but in some ways as the easiest. This concept of coherence turned out to be really important for us. We weren't confident that any single model we built was representing reality, and just because our training and holdout data did really well didn't mean that the model was actually going to work that well when we applied it to our real-world data. Not everybody has that challenge, but if you do have that challenge, building multiple models and testing for the coherence of the models is a great way to solve it. We were really pleased with this, and it really turned up some significant problems for us as we went through the process. And finally, and I just touched on this, operationalizing models is one of the most important things to think about when you think about re-engineering a machine learning process. Hey, there's so many different ways to do this now. It can be done in the cloud, it can be done on-premise, or in our case, everything we do is in the cloud, so it's one cloud instance to another. But this doesn't have to be a barrier to getting machine learning out there, but it does require the integration of data science and programming. It requires close cooperation between those two and a lot of communication. All right, we're done. I'm on Slack. I hope you'll join me. Give me a shout and let me know if you have questions, thoughts, or comments. I'd love to hear from you.
Thank you, Gary, for sharing this material. This has been an extremely enlightening presentation. Just a reminder to our guests, you can engage Gary Angel with questions or comments at his Slack channel on the Analytics Nexus Slack. Thank you again.